In this video, I'm going to cover examples 8, 9, and 10. And right away with example 8, we're getting into quadratic equations. Again, if you forgot all about quadratic equations, please review this topic, how to solve quadratic equations. Now, it says, example 8 says, write the following trigonometric expression as an algebraic expression. Okay, so what they want us to see is that we have a quadratic type of an equation here. So if I say, let's say x equals cosine theta, and then I substitute, right? I substitute x in for the cosine theta, then what is x? If x is cosine theta, what is x squared gonna be equal? I hope you guys are saying that that is cosine squared theta. So here in this expression, cosine squared theta is x squared. So when I make that substitution, what I'm going to get 2x squared plus x minus 1. And this is a quadratic expression. It's not a quadratic equation yet because it doesn't say equals something. When it does, that's going to be a quadratic equation. This is a quadratic expression. How do we recognize a quadratic expression? The quadratic expression, well, first of all, it's going to have a term that's squared, and then we're going to have the same term that's not squared. And a lot of times we're also going to have a constant, even though that's not a rule. The rule is for the quadratic expression just to have a squared something. But then this trio is classical for quadratic expression. So a trig function squared, just the trig function. It could be multiplied by a coefficient, like in this case we have 2, in this case we have 1. It could have other coefficients, of course, and then we're also going to have just a coefficient, a free coefficient, not multiplied by anything. So that's quadratic expression. Okay, what else is going to be useful in solving equations? Because that's where we're actually heading towards, solving equations. It's also useful to recognize the difference of squares, right? So here it says rewrite the trigonometric expression using the difference of squares. What is a difference of squares? Well, it's the expression of the type a squared minus b squared. And I will remind you that that will equal a minus b multiplied by a plus b. That's the formula. That's how we can factor expressions like this. So it's actually very useful to see them when we have them. So I think a lot of times students don't see this expression as a difference of squares because they don't recognize that one is a square, because we need to have a square and a square. Like full cosine square, usually when I ask them, it's a square of what? If we unsquare full cosine square, we're going to get 2 cosine theta, right? That's 2 cosine square theta squared. But as for 1, well, 1 is also 1 squared, right? Don't forget that 1 is a perfect square. It is also a perfect cube or perfect fourth power. Why? Because 1 squared is 1, 1 cubed is 1, 1 to the fourth is 1. So 1 could be any power. So it is a square. All right. So yeah, so how do we rewrite it as a difference of squares? Well, we're gonna have 2 cosine theta plus 1 multiplied by 2 cosine theta minus 1. All right, so I want you to practice that and to rewrite 25 minus 9 sine squared theta as a difference of squares. Go ahead and pause here. And we're going to continue to example number 10. And let's take a look at this example together. Now, this one, honestly, it's a little bit misleading because we are talking about difference of squares, and this is obviously the difference of squares. So be honest with you, the first time I saw it, I jumped on the difference of squares right away. But as it turned out, you can do it that way, but it's not the most efficient way. So just rewriting, noticing that cosecant is 1 over sine. So cosecant square, we're going to have 1 over sine square. And cotangent is cosine over sine. So again, cotangent square is going to be cosine square theta over sine square theta. So we have a common denominator here. So simplifying, this means that we can combine the fractions. We're going to have sine square in the denominator. In the numerator, we're going to have 1 minus cosine square theta. And that 1 minus cosine square theta is our Pythagorean identity, right? And so that gives us the sine squared in the numerator. And then we also have the sine square in the denominator. So that will be equal to 1. And voila, we simplified our expression without applying the difference of squares formula. And it's very simple. So actually, we could do it through the difference of squares as well, but it would just take us a little longer. Okay, so that was the last one for this section, and I want you to try this one by yourself. It says use algebraic techniques to verify the identity. And if so, pause here and try it by yourself. And if you tried already and you're unsuccessful, then try to apply this hint, which says multiply the left side, the denominator and the numerator, by the conjugate of 1 plus sine theta to get 1 minus theta. This way, you can use your difference of squares formula, and you're going to get there. And I'll see you in the next video, section 9.2.